In the next section, 6.2, we're going to look at confidence intervals for means with small samples. In 6.1, we found confidence intervals by calculating the margin of error E using ZC because one of the following were true. Either the sample size was 30 or more, in which case the central limit theorem applied, or we knew the population standard deviation, sigma, and the population from which we were sampling was normally distributed. In many real-life situations, we won't know sigma, and we cannot afford to take a large sample size. Hence, we cannot use S, which is the sample standard deviation, in place of sigma. This means that in order to construct confidence intervals using small samples, we have to make a change. And the change that we're going to be using is we're going to swap out the standard normal table for a new distribution, which is going to be called the T distribution. Whereas the standard normal distribution relied on two values, or a normal distribution rather, relies on two values, namely the mean and the standard deviation, this brand new distribution, the T distribution, is going to depend upon a parameter which is going to be called the degrees of freedom. Okay. So what is the T distribution? Well, when the sample size is small, in other words less than 30, it's the distribution of sample means is not going to be exactly normal, and instead it produces what's called a T distribution. The T distribution has a lot of similarities to the standard normal distribution. First of all, it's going to be bell-shaped. It will also be symmetric about the mean. It will also have a total area under the curve of 1. The mean, median, and mode will also be equal to 0. And its exact shape, there's several different T distributions corresponding to what's called the degrees of freedom. The degrees of freedom will abbreviate DF. It's always one less than your sample size. So if we have a sample of size n, then the corresponding degrees of freedom, DF, is going to be equal to n minus 1. In this graph, it might be a little bit difficult to see because it's black and white, but there's two T distributions. One is the one in black, which I'm tracing along with my cursor. This corresponds to 2 degrees of freedom. There's this curve here, which would correspond to 5 degrees of freedom. And then the last one is the normal distribution itself. One of the things that happens is as the degrees of freedom increase, the corresponding T distributions that we get closer and closer and closer to the standard normal distribution, so much so they're almost indistinguishable once degrees of freedom hits 30. So for that reason, that's why when a sample size is 30 or more, we always use the normal distribution. We don't have to resort to the T distribution. Okay. The T distribution is similar to the standard normal in that it is symmetrically distributed around the mean. However, the T distribution varies from the standard normal in that its standard deviation is determined by what is known as the degrees of freedom. So just kind of like how we are finding the z-critical in the last section that involved an inverse normal command, we're going to be able to find a t-critical value corresponding to a certain confidence level in a t distribution with a given number of degrees of freedom. Okay. This will be the one spot in the entire class where there will be some difference in variability between those of you using a TI-84 calculator and those of you using a TI-83 calculator. Okay. Let's look at the first example together, and I'm going to show you how to do this both ways. For example, let's suppose that if we have a sample of size 10. In a sample of size 10, the corresponding T distribution would have 9 degrees of freedom. It's just going to be 10 minus 1, which is 9. If we wanted to find the T critical value that would correspond to the 95% confidence interval, we can use the following brand new command in the calculator. It's going to be inverse T. This is only located on the TI-84. The TI-83 will not have this command. We would go to second distribution. We would go down to inverse T. And then inverse T is going to ask us for two things. They want to know the area, which once again will be the cumulative area, meaning the area to the left of a T critical value, and the degrees of freedom. Well, if we want to be at the 95% confidence level, then that's the amount that's going to be in between negative TC and positive TC. So if I want the amount, let's say to the left of the negative T critical, I would do the whole 1 minus 0.95. That would be the amount in the two tails. If I were to divide that by 2, that would give me the area in one tail, which would work out to be, let's see, 1 minus 0.95 is 0.05. If I divide that by 2, I'm going to get 0.025. That would be the cumulative, i.e. the left tail area. We said it was 9 degrees of freedom. We go ahead, hit paste, and hit enter. And it gives us a T critical value, which will round to 3 places, of 2.262. 2.262. Remember, technically speaking, whenever we talk about whether it's a Z critical or a T critical, we want the positive value to be used. So we need to just switch this to make it a positive value. For those of you that have the TI-83, how would you be able to do this? Well, the answer is there's a T-score chart. This T-score chart works as follows. We have the degrees of freedom, which is the DF going down. You would trace down till you get to the desired degrees of freedom. In this case, we're working for 9 degrees of freedom. And then you can do one of two things. You can use the same one-tail area that those using the TI-84 would have to use. We said it was 0.025. Trace that down to 9 degrees of freedom, and we get 2.262. Even easier than that, for those of you that want to use the table approach, you don't have to calculate the whole 1 minus C divided by 2 thing. They directly have the level of confidence as a top row of this column. So if they say, okay, I want you to be confident at the 95% level, you go to 0.95, then just simply trace it down to the 9 degrees of freedom, and that's how you can get the T critical score by using this chart. This chart you can use for the next exam. I also have the formulas for this chapter included at the very bottom. And where you can find this chart, I've posted it in D2L. It's attached to this current week's news announcement, and it's also under the content tab in D2L. You can find this under the class notes. We have all of the notes for the course, and then at the very bottom is this T distribution chart that has the formula sheet as well. Let's do another one of these. Suppose we have 7 degrees, assuming a sample of size 7, and we want to find the T critical value that would correspond to the 99% confidence interval. If I do this using the calculator, first of all, note that if n is 7, then that's going to produce 7 minus 1, or 6 degrees of freedom. For the tail area, second distribution, going down to that choice 4 inverse T in the TI-84 calculator. The tail area in this case would be 1 minus 0.99, which would be 0.01 divided by 2, which would be 0.005. 6 degrees of freedom. Go ahead and hit enter, and this should produce a T critical value of 3.707. So 3.707. Alternatively, if we wanted to use the chart, we have 6 degrees of freedom, so we come down to the DF of 6. We can just simply look up to the confidence level we want, which is the 99% confidence level. So 6 degrees of freedom, going over to that 99% confidence level, would again show us that the T critical value here is going to be 3.707. So one of the fundamental questions that we have to answer, and this is going to be the thing that you're going to be faced with, especially when you take the next test, is a lot of these questions are going to sound very similar between 6.1 and 6.2. They will ask for things like find the margin of error or construct a certain confidence interval. What will be important for us is knowing whether or not we need to use a Z distribution or a T distribution. Okay. First of all, if our sample size is large enough, meaning if the sample size is 30 or more, then we will automatically be using the normal distribution. However, if our sample size is small, meaning less than 30, then we have a couple possibilities. if we know that the information is normally distributed and we have the population standard deviation, that will still allow us to use ZC, or the normal distribution, from 6.1. The situation where we will specifically be using this brand new t-distribution is when we have a small sample size, meaning n is less than 30, and we don't know the population standard deviation. So we don't know sigma. All we have is a placeholder for it instead, as a substitute would be the sample standard deviation, which would be S. So that's when we would use the t-distribution. Let's take a look at example 1. They don't actually ask us to solve anything, just to determine whether we would use a t-distribution, a normal distribution, or neither. In example 1, part A, we have a sample size of 15, so it is a small sample size. However, because we know sigma, which is the population standard deviation, that will allow us to use the z-score. So for that type of problem, we would use a z-critical score. In part B, we have a sample size of 20, so it's another small sample size because it's less than 30. And this time we don't know sigma, we only know the sample standard deviation. So this is the case where we would use a critical t-score. In part C, if n is 40, I can stop right there. Because n is 40, more than 30 or more, I automatically know I can use ZC. It wouldn't matter whether you had S or sigma in that case. 30 or more automatically makes it a z-score. In part D, we're close. We don't have the 30 we need. So n is less than 30, and we only have S. We don't know sigma. So that would be another situation for using the t-score. And for the last one, we just make the cutoff of 30 or more. And in addition, we also happen to know sigma, but 30 or more automatically is going to be ZC. It wouldn't have mattered whether this had been sigma or S. As long as it's 30 or more, that's the benchmark for using a z-score. The next thing we're going to do is construct confidence intervals by using this t-distribution. And the methods that we're going to employ will follow identically to those we just used back in 6.1. We want to pick a sample from the population. We can calculate the mean of our sample. That'll be x bar. And then in order to create the confidence interval, the confidence interval is going to be of the form x bar minus e to x bar plus e, where in this case, the margin of error will be computed as TC times S divided by the square root of n. In the previous section, 6.1, the formula for E was ZC times sigma divided by the square root of n. Here, if we're using a t-score, the t-score will replace the z-score in the formula, and oftentimes we'll have S as a stand-in for sigma.